All right, so here we're going to do part 2 of talking about vibrational spectroscopy. Okay. So, right where we left off in part 1, right, we talked about how the change in energy is related to h bar omega or hc nu tilde. Okay. Right, how the change in quantum number V is plus or minus 1, right, which means that there's only one peak for a given vibration, okay. That's assuming a perfect harmonic oscillator system, okay. Now, we know typical bonds are not perfectly harmonic, right. For low quantum numbers, they look harmonic, right, but then when you get up to higher quantum states, right, you start to get this anharmonicity effects going on, right, where the energy levels are no longer equally spaced and become smaller and smaller spaced, right? And so the impact of these anharmonic effects is, again, that the energy gap is not the same between all states, okay? Which means that this energy gap here, delta E, h bar omega, right, at the top of the screen, right, that energy gap is not going to be independent of the quantum number, okay? And so because of that, you'll have more than one peak that will appear, right, depending on what your initial and final vibrational states are in that peak, okay? And then these inharmonicities can also cause certain vibrational transitions that wouldn't normally occur to occur, meaning like you could have delta V, right, equals plus or minus 2, for example, okay? Right, and so there's kind of a couple of different things that can happen for kind of these anharmonicity effects, right? And typically, you know, if we're looking at just typical IR spectras, you're not looking into great detail and really trying to get fine detail on those spectra, right? We kind of just assume harmonic. We assume most things are in the ground state, so you're just looking for the fundamental transition, you know, V equals 0 to V equals 1 transition, and in which case, right, you're focusing on kind of this one dominant peak, okay? Again, most states are in the ground vibrational state, so that fundamental transition should be most dominant, right? And higher energy transitions in these anharmonicity effects, right, will not be as obvious or as easily observed in a given vibrational spectrum. All right, so let's talk about vibrational Raman spectra, okay? So the gross selection rules, right, for vibrational Raman transition is that the polarizability should change due to the molecular vibrations, okay? In this, I don't have a great way of trying to visualize it and tell it for you, if I'm being perfectly honest, right? This can be very difficult to tell visually by looking at a vibration, okay? And a lot of times how we determine this is we just look at the symmetries of the molecules and vibrations. So this is something that you'll do here at Texas State for inorganic chemistry when you take the advanced inorganic class. You'll talk more about symmetries of molecules and their point groups and character groups and things like that, and be able to kind of predict what different vibrational transitions will have certain Raman spectra or not, and what molecules will or won't have IR or Raman spectra based off the symmetry of the molecule. Okay. Right. The specific selection rules for Raman spectra are going to be the exact same. Delta V is plus or minus 1. Okay. There will be a Stokes line at delta V plus 1 and an anti-Stokes line at delta V minus 1, right? But like unlike vibrational, right, or rotational, right? Rotational spectra, right? If I plotted like a rotational spectra, right, I had this Rayleigh line that's just pure scattering, and then I would have, you know, many lines going kind of away from this, right? This is pure scattering here, right? Delta J equals 0, right? There's no change in your rotational state for your molecule or things like that, right? And we'd have our Stokes and anti-Stokes, right? This would be Stokes. This would be the anti-Stokes, right? Okay, and I have multiple peaks for these guys, right? But In the case of the vibrational spectra, okay, so if I were to do a vibrational spectrum, right, do the same thing, I'd still have this scattering, okay, delta V equals 0, but then I would just have one peak for the Stokes and one peak for the anti-Stokes. And here's Stokes, right? So again, I'm only going to get one peak because my change in energy, right, is still just that h bar omega, right? Still independent of my quantum number, okay, right? And the shift between your Rayleigh line here, right, and say the Stokes, and the shift between the Rayleigh and the anti-Stokes, this is going to be the same energy gap, right, between these guys, right? But the Stokes line will have a much higher amplitude than the anti-Stokes, right? And the reason that is just because the population of the states for the anti-Stokes line is very small, right? Because for the anti-Stokes line, you're going from quantum number V equals 1 to quantum number V equals 0, right? And so there's just not nearly as many molecules in the higher energy vibrational state than there are in the ground state. So you're just not going to have as many transitions occurring from V equals 1 to V equals 0 because the molecules first have to be in V equals 1 for that transition to even occur. Okay? Right. So let me clear the writings on the slide just so you can see, right, what's kind of typed up here, right? So I'm just kind of reiterating what we were just going over as to why there's a higher amplitude for the Stokes versus anti-Stokes, right? And then we talked about, right, why the harmonic oscillator approximation, they're just two lines. Actually, so these two lines will not appear on top of each other, right? They will be shifted, and so this is not true. There's going to be two lines, but they won't appear on top of each other. Okay, there will just be two lines. All right, so now for a couple quick questions, right? So here, which of the following molecules does not absorb in the infrared? Okay, so to absorb in the infrared, that's a vibrational transition, okay, right? And basically you need to have some sort of vibration that's going to induce a dipole moment in your molecule, and that's just never going to happen for I2, okay? CCl4, it can happen. Certain vibrations will induce a dipole moment because it will break sort of the spherical symmetry of the molecule. In H3, there will definitely be vibrations that change the dipole moment. HI will for sure as well. So I2 will not have any absorption spectrum. Okay. So in the harmonic oscillator approximation, only a single line appears in the absorption spectra for linear molecules. Reason or reasons for this include what? Okay, so here the energy levels are equally spaced. Okay, that is definitely has to be the case. Okay, so if your energy levels aren't equally spaced like rotational states, then you get many peaks appearing. Okay, the selection rule is that you can just have a plus or minus 1 change. That also is a reason why there's only one peak. The molecules have a changing dipole moment. That's not really the reason why there's only one peak. Okay, so it's not C, but A and B are both true, so D here, 2 or more, are true. All right, and so then just a question here. I'm going to look at the relative number of Br2 molecules in the ground in first excited vibrational state at 300 Kelvin and 800 Kelvin. Okay. We're given that the frequency or the wave number of that vibration is 321 inverse centimeters. Okay, and right, and we want to use that Boltzmann distribution. Okay, here I don't have any degeneracy here because right for vibrational states they're all non-degenerate, so the degeneracy is always just equal to 1. Okay, and so to solve for this, right, we just need to look at P0 divided by P1. Okay. Find the relative ratio of the ground state versus the first excited state. Okay, so you plug that in, right, and it just simplifies down to right e to the minus energy difference or kT. Okay, right, that energy difference, right, is just given by Hc times the wave number, right, for your system. And so if we plug in what that wave number is in terms of inverse meters, and then plug in for the values of Hc and K, we'll get this lovely equation here that we got to plug in and simplify down, right? When you do that, you get the ratio of P0 or P1 is, right, e to the 462.38 divided by t. And so at t equals 300, right, so plug in 300, simplify, and t equals 800, plug in 800, simplify, right, you see that it's, right, roughly 5 to 1, you know, ground V equals 0 to V equals 1 occupation, right? At 800 Kelvin, then you're starting to get kind of a 2 to 1, right, ratio of V equals 0 to V equals 1, right? So, right, you need to get to definitely higher temperatures than room temperatures to have significant population of V equals 1, okay? Right, again, there are going to be, even at room temperature, which is not quite 300 Kelvin, but close enough, right, there are going to be some molecules in the V equals 1 state, right, but it's not, right, it's not, like rotational states, it's very, very different, okay, because of the gap between these rotational states. For vibrational states, it's large enough that there's only small occupations of some of the excited states at room temperature. For electronic states, when we talk about that, there's no occupations of the excited states at room temperature. Okay? And so that will be it for vibrational spectroscopy. Okay. We'll talk, I guess, not sure. That's it for, you know, this lecture. We'll talk a little bit more about vibrational spectroscopy in the next video, as well as vibrational rotational spectrum, right, in the next video.